Compact sets work very well with continuous functions. Here, this theorem is going to be very important in the sequel. Here we have two metric spaces. X is compact, and we have a continuous function from x to y. Then we know for sure that f of x is compact. So how is the proof? Here we want to show that f of x is compact. And what we have is f continuous, x compact. Okay, so according to the definitions, we need to show the compactness of f of x. So what does the definition say? The definition says that if we take an open cover V alpha of f of x, we need to show that there exists a finite subcover. Okay, here, this is what we need to show. And the only two things that we have available are the continuity of f and the compactness of x. So somehow we have our f of x here that lives in y. And here we have x. Okay. And somehow we have a cover here of this one of f of x. And the only way we can hope we will be able to get the finite subcover is to send everything back to x. Okay, so we are going to, these are our v, let's use green here. These are the v alphas, and then we need to bring them back to x. Okay, here will be a mess. Okay, these are the preimages of the v alphas, and then here what we are going to do, we are going to select a finite subcover. Okay, whatever that is, and then we are going to send it back forward to whatever covers f of x. Okay, that's the way we are going to get the finite subcover. Again, we are going to just send the whole cover v alpha back to x using the inverse of f, then use the compactness of x to say, well, okay, there is a finite subcover by this f minus 1 of the v alpha. And then for those, we are going to send them back forward, and those will give me the finite subcover of f of x. So that's the idea. Let's put the math here. We need to use the continuity to send the cover v alpha back to x. So, but how does that work? Notice here that because f is continuous, one of the most important properties of continuous functions is that for the pre-image of an open set is open. Here we are using that v alpha is open. Now, because the v alpha covers x, f of x, that means that the inverse image of the v alphas covers x. Okay, but x is compact. That means there exists a finite subcover f minus 1 v alpha 1, f minus 1 v alpha 2, f minus 1 v alpha, let's say n. Okay, notice here we have already used the continuity of the function f and the compactness of x. Okay, so we already have a finite subcover of x. Okay, so then what we are going to do, well, let's write it carefully. That means x is contained in the union of these open sets that are the inverse images of v alpha 1, v alpha 2, and so on. Okay, but then that means that f of x is contained in f of the union, okay, which is contained in f of f minus 1 v alpha 1 union f of f minus 1 v alpha n, okay, and here we use that f of f minus 1 v alpha 1 is contained in v alpha 1 union v alpha 2 union v alpha n. Here we used f of f minus 1 of a contained in a. This is true for every set, and it is an equality if the function is surjective. Okay, and this is what we wanted to prove, because this shows that from the original cover v alpha of the set f of x, we can extract a finite subcover v alpha 1, v alpha 2, v alpha n, such that f of x is actually contained in the union of those. Okay, that's the definition of subcover. So this completes the proof. Now, there are some important consequences of this theorem. The first one, if we have a function f, a vector function from a metric space into Rk, and x is compact, okay, x compact and f continuous, those are the two things we need, then the image of x by f is closed and bounded. Okay, and also f as a function is bounded. Now here, let me define what do I mean by vector function being bounded. Okay, that is, so a mapping f from E into Rk, it can be any set, is bounded if there is a real number m such that the modulus of f of x is less or equal than m for all x in E. Okay, so that's the meaning of bounded for the mapping vector f. And actually, the proof of the theorem is quite straightforward. Let me put this a little closer together so that we can, there we go. So I was saying the proof is very easy because it follows from the previous theorem and Hein-Borel. the previous theorem is saying that f of x is compact in Rk, and Hein-Borel says that compact is in Rk if and only if closed and bounded. That gives the first part, but then once we know that f of x is bounded, that means that for every little x in X, there is some bound, and that is precisely the definition of a mapping being bounded. Okay, so actually you see that the proof is just writing down the definitions carefully. There is, so this theorem actually, it's very important when we discuss real functions, okay? Because that is what we have seen in calculus as the extreme value theorem. So if we have a real function in a compact metric space, okay, this is continuous, and we have x compact metric space. Okay, it's very important that it is compact. Okay, we will be able to show counterexamples of this theorem whenever the function is not continuous or x is not compact. Okay, but what we have here is that there exists points PQ in X such that f of p equals the supremum of f of p, p in X, let's call them little x, for example, and then f of q is the infimum of f, all right, that didn't work out, infimum of f of x, x in X, okay? So what we are saying here, this is the extreme values theorem. What we are saying is that if the function is continuous over a compact metric space, then we are guaranteed that the function is going to attain the supremum and the infimum in the set X, in the metric space X, okay? And remember, we know from Calc 1 that if the function is, let's say, we work between 0 and 1, okay? Then the function may be continuous, but it may happen that the supremum and the infimum are not attained, okay? Are not attained because they are infinity and negative infinity. Or otherwise, we could have something discontinuous. We could have x that is 0, 1, that is closed and bounded, so it's compact. Okay, but we have a discontinuous function. It may happen here that if the function is discontinuous, let's say it has a jump, okay, it may have a minimum, the infimum may be attained, but the supremum will not be attained, okay? So no p such that f of p equals the supremum of f of x, x in 0, 1. Okay. This theorem can be stated in a different way. We could also write it like this. We could say that there exists PQ in X such that f of X is in between f of Q and f of P for every X in the metric space. Okay, that means that f attains its maximum at P and its minimum at Q. And actually, the proof of the theorem, we don't need to write it, because actually the previous theorem says that f of x f of capital X is closed and bounded, and we already saw in chapter 2 that then it must contain a supremum and infimum. Then f of X contains the supremum of the f of x's and the infimum. Okay, so that's the way we use the previous theorem to show this fact.